This is AP Calculus AB. We're on worksheet 5-8 for piecewise integration. Integral 1, we're trying to find the integral between 0 and 4. So 0 is going to be this spot right here. 4 is going to be this spot right here. Let's go ahead and just connect those to make it a little bit more obvious what's going on. And again, we're just trying to find the area underneath the curve. So let's go ahead and separate this into a few different pieces. The first piece that I see is that there's this triangle that has a length of 2 by 1. So this rectangle will be 2 times 1, which is 2, but the triangle is half of that. Therefore, the triangle is an area of 1. This rectangle down here is 4 by 1. 4 times 1 is 4. Adding 1 plus 4 gives us an area of 5. And number 2, what do we have happening? Number 2, we're going between 0 to 4. Okay, so 0 is going to be this spot right here, and 4 is going to be this spot right here. Let's go ahead and connect these lines together. Straight line. Haha. All right. And then we need to do this. All right. What do we have here? We have a rectangle that is 1 by 2. 1 times 2 is 2. Okay. This triangle is 2 by, okay, it's going to go 1, 2, 3, 4. So 2 times 4 is 8, but half of 8 is going to be 4. And then down here we have a 1, 2, 3 by 2, which is 6, but it's down beneath the x-axis. So it's a negative 6. Adding all this together gives us 0. Nice. All right. Moving on to number 3. Number 3, we have a piecewise function. So again, whenever we have a piecewise function with no graph, instead of doing area, you're going to just take the antiderivative of each piece. So your first integral is going to be between 0 and 6 of your left piece, the 2x plus 4. And the right integral is going to be, do I want to write it down here or right here? Let's go ahead and do it off to the side. We'll say the integral between 0 and, oh, I need to change my bounds here because our bound doesn't go to 6 anymore. This one ends at 6 up here, and my integral symbol is not the most pretty. There we go. So my second piece is going to go not from 0 to 6, but from 2 to 6, and this one's going to go from 0 to 2. So essentially, if I do go from 0 to 6, it's cut in half by this suspect point, or wherever you glue those pieces, those left and right pieces together. So now I have the correct bounds on everything, and now I can take the antiderivative of each piece. I'm just going to work down from here. All right, antiderivative of 2x is going to be x squared. Again, it was x squared divided by 2, but the 2 and the 2 cross-canceled, so I didn't show that step. And antiderivative of 4 is 4x. All right, and that's going to be evaluation bar between 0 and 2. Let's move on to this piece right over here. Okay, antiderivative of x is x squared over 2. That's evaluation bar between 2 and 6. All right, and let's go ahead and see what happens when I plug in 2. When I plug in 2, I'm going to get 2 squared plus 4 times 2. And I'm going to, I think the best way to do this is I'm going to say x equals 2 is going to go right here. And I'm going to say when x is equal to 0, I'll go right here. And I'll say this is going to be 0 squared plus 4 times 0. This is going to be 0, of course. And then I'm going to have a 4 plus 8. 4 plus 8 is 12. And then I'm going to subtract those two. So this piece is 12. And now I'm going to move over to this right-hand piece. Okay, so I'm going to plug in 6 first. So I'll say when x is equal to 6, what do we have happening? This will be 6 squared over 2. And when x is equal to 2, I'm going to get 2 squared over 2. All right, simplifying these a little bit more. 6 squared is 36. 36 divided by 2 is 18. And 2 squared is 4. 4 divided by 2 is 2. And again, we're going to subtract this minus this. 18 minus 2 is 16. Adding together 12 plus 16 is 28. So I'll say 28 for our final answer. And box it. All right, what about number 4? And number 4, again, we're going to be splitting the integral into 2 different pieces. So I'll say that this is really the integral, whoa, pen, come on, work. The integral from 0 to our suspect point 2, plus the integral from that same suspect point 2 to the end of the interval. I'm going to do my left piece, x minus 3. I'll do my right piece, 2x plus 1. All right, do we have to pay the tax man? No. I guess I should have checked the last one. I don't have to pay taxman because there's no house here for the taxman to even knock on the front door of. You need like a power house or a trig house or a function house or something like that, or a general house is what we're calling it. All right, so let's take the antiderivative of x plus 3. That's going to go up to x squared divided by 2 minus 3x. Evaluation bar between 0 and 2. Antiderivative of this right piece. Let's see, it's going to be 2x is going to go to x squared. Again, I did a hidden, there was a 2 that I brought down here, but I divide by 2 because this 2 comes down here, and the 2 and 2 cross cancels, leaving behind just the x squared. Plus 1 is going to be plus x, and then this is evaluation bar between 2 and 4. All right, what happens when x is equal to 2? And when x is equal to 0. When x is equal to 2, I'm going to get 2 squared over 2 minus 3 times 2. And that's going to be, let's see here, this is going to be 4 divided by 2. All of that turns into a 2 minus 6, which is a negative 4. And down here when x is equal to 0, I'm going to get 0 squared all over 2 minus 3 times 0, which is 0. All right, so if I subtract those two pieces, I get a negative 4. All right, let's work on this right-hand piece now. Right-hand piece is when let's do x is equal to 4 first. When x is equal to 4, I get 4 squared plus 4. That's going to be 16 plus 4, which is 20. Equal to 20. And then when x is equal to 2, what happens? I'm going to get 2 squared plus 2. And that's going to be 4 plus 2. 4 plus 2 is 6. So when I subtract those two, I get 14. All right. And 14 minus 4 adds up to a total of 10, which I can box down here. I ran out of room up here, so I couldn't write it. All right, let's move on to number 5. Again, left and right piece. Let's go ahead and do our integrals first. Integral between 1 and the suspect point of 3, plus the integral from that same suspect point from 3 to the end, which is 5. Okay, first piece is 2, the right piece is x minus 1, and I'm always worried about paying the tax man whenever I have an antiderivative, but I don't have to pay the tax man. There's no house. So antiderivative of 2 is 2x, and that's going to be evaluation point between 1 and 3. And by the way, whenever you have the integral of a constant, I hope that you have the shortcut for that. Maybe I'll talk about that over here after I do it the long way. I can tell you right now that the answer here is going to be 4, just doing math really quickly. Like I can see this and immediately jump to 4 as an answer all in my head in under a second. So I'll do that in a second. So first I'm going to say when x is equal to 3, it's going to be 2 times 3, which is 6. And when x is equal to 1, I'm going to get 2 times 1, which is 2, and then I subtract those two and I get a 4. So that's a lot of work. So what would you do next time? And this is maybe something that we should turn into a flashcard, right? We should say that whenever I have the integral from, we'll just make it more generic, from a to b of some number without a variable. So there's no x, right? There's just a number, a constant. The answer here is you always just subtract the bounds, b minus a, and then multiply it by whatever the number is. So here's what I really did for this problem. I said, okay, 3 minus 1 is 2, and 2 times 2 is 4. That's the math I did. I didn't do all of this antiderivative stuff. That's too much work. So please be using that in the future. And if I forget to remind you guys, make sure that that is a card in your flashcards. All right. Over here, we have antiderivative, which is going to be x squared divided by 2 minus x, evaluation bar between 3 and 5. Let's see what happens when x is equal to 5. When x is equal to 5, I'm going to get 5 quantity squared divided by 2 minus 5. And when x is equal to 3, I'm going to get 3 squared over 2 minus 3. Simplifying both of these, let's see, this is going to be, this is going to be yucky. It's going to be 25 over 2 minus 5. Oh, but this one's also going to be an odd number over 2, so I'm going to leave it like this. Watch this. So I'm going to say this is 25 over 2 minus 5, and this is going to be 9 over 2 minus 3. So I kept it as a fraction, didn't try to combine these into one fraction. What you could do, you can say this is 10 over 2 and combine them. I think it's faster to now subtract these two, right? If I do 25 over 2 minus 9 over 2, those are like fractions. They're like denominators, so I can subtract the fractions. 25 minus 9 is 16, and it's still over 2. So I'm going to say when I subtract these, I'm going to get 16 over 2. And I'll also subtract this one. So I have a negative 5 minus a negative 3, so this is really plus 3, right? And that turns into a negative 2. And this 16 over 2 turns into an 8. So it's 8 minus 2, which is 6. So this is equal to 6. And then you add those two pieces together. You have the left piece, you have the right piece, you add them together, and you say, 4 plus 6 is 10. I don't know what I'm writing for, though. 10. Ta-da. All right. And moving on to number 6. Number 6, oh boy. So it's kind of interesting. When x is equal to 0, there's not area associated with that, because whenever I'm equal to a certain point, that's just a point on a graph. There's no area underneath a point. So I kind of don't worry about it. So I'm going to cross it off. Whenever you have just at one single point, x equal to a number, you ignore it in terms of an area. But I still need to do the antiderivative. So what am I going to do here? There's a left piece and a right piece. The left piece is going to go from -1 to 0. I'm going to say from -1 to 0 of the left piece, which is x squared. And I'm going to add together the right piece, which is from 0 to that positive 1. Left piece is x squared, I already said that, and right piece is x. Do I have to worry about paying the tax person? I mean, kind of. There is a house now. Here is the house, and it's a powerhouse, but the derivative of the inside of the house, the dinner, is 1, therefore I can avoid paying the tax man. But I should always be double checking whenever I see that integral symbol. Worry about the tax man. He comes for you. All right, so this is going to be x to the power of 3 over 3, evaluation bar between -1 and 0, and this right piece is going to be x squared over 2, evaluation bar between 0 and 1. All right, so from here, let's go ahead and plug in. When I say x is equal to 0, I do that piece first. That's going to be 0 cubed over 3, which is equal to 0. And when x is equal to a -1, I'm going to get a -1 to the power of 3 over 3, which is equal to a -1/3. I subtract those, which means I have 0 minus a -1/3. Double negative becomes plus, and I really have a positive 1/3 down here. Let's go ahead and do the evaluation bar for the right-hand side. When I evaluate, I'm going to say x is equal to 1 first. That's going to be 1 squared over 2, which is 1/2. And when x is equal to 0, this is going to be 0 squared over 2, which is 0. Subtracting those two yields 1/2. A half plus a third is, what is that, 5/6, right? I was just doing some math really quickly in my head. I said 2 over 2, 3 over 3. So I'm really adding 2/6 plus 3/6, and now that I have like denominators 6 and 6, I add the numerators. 3 plus 2 is 5, and the final answer here is 5/6. I ran out of room here, so let's go ahead and move all of that stuff to the left a little bit, and I'll say adding these together gives me 5/6, and I'll box my final answer. All right, moving on to the backside. On the backside, what do we have? All right, we have the left piece, which is 0 from 1, plus the right piece, which is from 1 to 2. All right, on that left piece, I have e to the power of 2x. On the right piece, I have e to the power of x. All right, now, again, I'm really worried about houses. So my house is right here, e house, tree house. The inside has a derivative of 2. It's not 1, therefore I do have to pay the tax man. You guys are probably good at doing that in your heads, but let me just do one of them really quickly in case you forgot. You need to figure out who u is, you need to figure out who the tax man is, and you need to figure out who u prime is. So u is 2x, the tax man, I don't see anyone, therefore it's 1, and u prime is 2, therefore you're paying the tax man this rate of 1/2, and my new integral really becomes the integral of 1/2 of e to the power of 2x. When I take the antiderivative of that, that is going to, e house is nice, right? It stays e houses. Whoa, why did you do that? That turns into 1/2 e to the power of 2x, and then evaluation bar with whatever your bounds are, and the bounds were 0 to 1, so I'm going to say 0 to 1. All right, that evaluation bar is ready to go, and then I move on to the second piece before I go all the way with this one. For my second piece, I do have a house, but the derivative of the inner is 1, therefore I can avoid paying the tax man, and I can instead just take the antiderivative, and done, it's e to the power of x. And again, evaluation bar between 1 and 2 for this one. All right, and these two pieces are going to be glued together. Let's go ahead and do the evaluation bar now. When I plug in 1 first, I'm going to say when x is equal to 1, that means I'm going to have 1/2 e to the power of 2 times 1 technically, but 2 times 1 is 2. And that's going to be e equal to 1/2 e to the power of 2, or e squared. And when x is equal to 0, you might be tempted to say, the answer is 0. But whenever you have e house, that's usually not the case. In this case, I have 1/2 e to the power of 2 times 0. And you'll remember that 2 times 0 is 0. And anything to the power of 0 is 1. This whole thing is just 1. And this 1 times a half is a half. Therefore, it's a half. And I don't know why I did that in red. Let's go ahead and say 1/2. All right, and then if I subtract those two, I'm left with 1/2 of e squared minus 1/2. Okay, and what about the evaluation bar for this right piece? Well, when x is equal to 2, I get e to the power of 2. Done. Okay, when x is equal to 1, I'm left with, I don't know, I have an equal to sign there. It should be a colon. There we go. This is e to the power of 1, which is just e. So when I subtract those two, I get e to the power of 2 minus e. Okay, so these two pieces are added together. You always add the left piece with the right piece. So these two pieces are also going to be added together. And let's see what that final answer is going to be. Can I use my shrink right here? Maybe I'm going to go ahead and do this. I'm going to say all of this is like side work for paying the tax man. And you guys can now slide up. All right, now I have plenty of room, and I can add these together. Well, I notice I have some like terms. I have an e squared and another e squared. So technically, this is 2/2 e squared. I'm just making like denominators with this 2 over here, and adding the numerators. 1 plus 2 is 3. So I can say over here, I have 3/2 e squared. I also have a minus e, and I also have minus 1/2 if I add everything together. Awesome. All right, and in number 8, what do we have? So E is roughly about, I'm going to say it's about a 2.7-ish. So I'm going to come and say that's bigger than 1, right? So I'm going to have my first integral between 0 and 1, and my second piece is going to be between 1 and E. All right, left piece is x, right piece is 1 over x, and I have to worry about paying the taxman. No house, so no taxman. This one kind of does have a house, but you might recognize it. This is the log house form. If you don't know this one, just really quickly, I can say this is the same thing as x to the power of -1. When you try to pay the taxman, you don't need to, because there's the powerhouse that you're kind of thinking it is. It's kind of a powerhouse, right? And you'll go ahead and say, okay, well, the powerhouse, this goes, you add 1, so you have 0, and then you divide down by 0, and you can't divide by 0. Therefore, you need another tool, and that tool is log house. So here's how you do this. This is going to turn into an x squared divided by 2 evaluation bar between 0 and 1, and this one over here on the right is going to turn into the natural log ln, natural log of the absolute value of whatever the inside is. In this case, it's just an x, and it's again evaluation bar between 1 and e. All right, so I have the two pieces. Let's do the evaluation. When x is equal to 1, what do I have? I have 1 squared over 2, which is just 1/2. And when x is equal to 0, what do I have? Well, I have 0 squared over 2, which is just 0. Subtracting those two gives 1/2. Over here on the left-hand side, when x is equal to e, I have the natural log of absolute value of e, and natural log of, well, I guess you worry about the absolute value if ever you have a negative on the side. Because this e is positive, I can kind of ignore it and say, okay, that's really parentheses, and the natural log of e, everyone should know this, is 1. All right, what happens when x is equal to 1? And that's kind of a fun question too. It's another definition of natural log that you should know. The absolute value of 1, again, because we don't have a negative, I can treat the absolute value as parentheses, and the natural log of 1, you should know as well, is 0. If you don't have those down in your flashcards, you need to add those. Again, subtracting the n from the start, 1 minus 0 is 1, and I have the two pieces which I can now add together, and 1/2 plus 1 is 1.5, or you can say it's 3/2 for my final answer. I prefer improper fractions over decimals, so that's what I choose. All right, what about number 9? Oh boy, some trig. Here we go. Again, left piece is from 0 to pi. The right piece is going to be from pi to 2 pi. And for the left piece is going to be sine of x, and the right piece is going to be cosine of x. All right, so from here, I'm worried about paying the taxman, but again, both the inners here are 1, so I can avoid paying the taxman, and I can just anti-differentiate. Sine and cosine always flip-flop, so I know, I'll worry about the signs in a sec. I know sine is going to turn into some sort of cosine, and cosine is going to turn into some sort of sine. The question is, which of these is negative? One of them is negative, one of them is not. So whenever you see an antiderivative, it stands for anti. Anti-same means change. You are going to change the sign right here. And same thing over here. This is anti-change, which means same. Therefore, it's going to be the same sign. This was a positive. This is still a positive down here. Again, don't forget your evaluation bars between 0 and pi. And then this is from pi to 2 pi. All right, let's go ahead and plug those in. When x is equal to pi, what do we have? We have negative cosine of pi. Cosine of pi is -1. Again, I'll go ahead and draw out, I think I'll need these two spots here and here. This spot is both 0 and it's also 2 pi. They're the same point, and this point over here is pi. Cosine is talking about how far left and right you're moving. So I've moved left the full distance that I can, therefore cosine of pi itself is -1, but I also have an additional negative, so this is -1, which is a +1. What happens when x is equal to 0, though? When x is equal to 0, I get negative cosine of 0. Okay, so cosine of 0, I already pointed out, it's right here. Cosine is how much left and right you're moving. You're moving right the full distance of the unit circle. You're moving right 1. So this cosine of 0 is 1, but don't forget about that negative. It's a -1. Again, what I'm doing is I'm doing 1 minus whatever this is. So it's 1 minus a -1. Double negative becomes positive, and I have 2 for this evaluation bar. All right, what about for sine of x? Again, you're going to say when x is equal to the end boundary, 2 pi, what do I have happening? I have sine of 2 pi. 2 pi, there we go. Whenever I have 2 pi, that's talking about this point up here, which is all the way to the right. Sine is not talking about left and right, it's talking about up and down. Sine is talking about how far we moved off the x-axis, and I have not moved at all. Therefore, sine of 2 pi is equal to 0. What happens when x is equal to pi, though? Then you're going to get sine of pi. Well, again, pi is over here on the x-axis. I have not moved up or down. Therefore, sine of pi is also 0. And 0 minus 0 is 0. When I add the left piece and right piece together, I get the value 2. All right, moving on to number 10. In number 10, I have the left piece, which is going to be -1 to 0, and the right piece, which is going to be from 0 to +1. The left function is x plus 1. The right function is cosine of pi. Again, I'm always worried about paying taxman, but taxman isn't there, is not there. Therefore, I can not to do this one. And this is weird because cosine of pi is not really a function. It's a value. So I'm wondering if this is a typo. I saw this exact same question on the AP test. And I'm pretty sure it is a typo, even though this is pulled directly from the AP exam. So there's one, I'll talk about that a little bit more when we get there. Let's do this left piece first. So I don't have to worry about paying the taxman, which means I can anti-differentiate. This is going to be x squared over 2 plus x, evaluation bar between -1 and 0. This right piece over here, I guess I have to talk about it now. So cosine of pi is just a number, right? We talked about it over here. We knew that cosine of pi was equal to a -1 because it's how far left I moved. I moved left 1. Therefore, this whole cosine of pi is really just a single value, -1. And then I can take the antiderivative of that and it becomes -x. I don't think I want to do that. That's probably a typo. Let's go ahead and assume it is a typo. I'm changing the problem on the fly right here. I think I'll change this for future problem. We'll say that this is cosine of pi x for the future problem, because now it becomes a lot more interesting, maybe? I think it makes it harder and it's more likely to show up on the AP test. So I'm going to say that this is cosine of pi x. I guess I didn't need to erase that. So now I have to pay the tax person, because now if I look at the inside of the trig house, there's my house right here, right? Inside is my inner, and the derivative of my inner, the dinner, is pi. It's not 1. Therefore, you have to pay the taxman. I want to do that work, not up there, but down here. I'm going to say u is equal to, it's pi x, and taxman is equal to, I don't see him, so 1, and then u prime is equal to pi, so I'm going to pay the taxman 1 over pi, and my integral now becomes, I'll say that this switches to the integral between 0 and 1 of 1 over pi cosine of pi x. Now that I've done that, I can take the antiderivative. Remember that antiderivative of change, anti-change is the same. This will be the same sign, and I can just kind of rewrite this. It's still the same 1 over pi, and instead of cosine, you flip-flop that between cosine and sine, so it's going to be 1 over pi sine of that pi x. Now that I've done that, I can do my evaluation bar between 0 and 1. And then from there, I can evaluate that. I can say x is equal to 1. What is that going to be? And that's going to be 1 over pi sine of pi times 1. And pi times 1 is just pi. Sine of pi, we did that problem already, right? Sine of pi is this point right here where you're not moving up, you're not moving down. Sine is asking what is the y-coordinate, and the y-coordinate is 0. So I can come here and just make a note that this whole thing is going to turn into a 0. And 0 times 1 over pi is still 0. So I can say this whole thing evaluates to 0. And when x is equal to 0, I realize I need to do the evaluation over here. I'll do that in a sec. So over here, I'm going to say this is 1 over pi sine of pi times 0. Well, pi times 0 is 0, so this is sine of 0, and sine of 0 is still 0. So this whole value is 0 again, and I can say this is still 0. That is not the case if it's just cosine of pi. I should really ask my cohort if they think that that's a typo or not. What about over here? When I have these bounds, I can say when x is equal to the end of this, 0, I'm going to get 0 squared over 2 plus 0, and that's going to be 0. When x is equal to -1, I'm going to get -1 squared over 2 plus the -1. -1 squared is 1. 1/2 is 1/2, and 1/2 plus a -1 is -1/2. All right, again, we are subtracting end minus start, so this is minus a negative. Double negative becomes positive, and I really have a positive 1/2 from this value. So a half plus 0 is 1/2 for my final answer. All right, what about in number 11? In number 11, I have the absolute value of x over x. Oh, when it's not equal to 0, and when it is equal to 0, it's 0. So I told you guys this in the past, that whenever you have x is equal to 0, that's just one single point, because there's only one spot, right? Therefore, this doesn't affect the area, and I can cross it off. But the question is, what is this doing? And I've talked about it in class at least this year in 2025. But this is an interesting graph, because any number that you put in to the right of 0, any like a 1 or 2 or 3, watch what happens. I'm going to have the absolute value of 3 over 3, or I'll have the absolute value of 4 over 4, which all evaluates to 1, which means if I have a graph, on the right-hand side of that graph, I have just a solid height of 1. And I don't know what happens at 0. What happens if you plug in a negative number, like -3 over 3? Well, the top is going, or sorry, -3 down there. You're going to get a positive over a negative, but it's still going to be 1. Just this case, it's a -1, and you really have this height down here. So this is really the graph of the absolute value of x over x, which you'll see occasionally on the AP test. So what's really going on here? You can basically treat this as another piecewise function within the piecewise function and say this is really two things. This is either going to be -1, or it's going to be 1. It's going to be -1 if x is less than 0, and it's going to be 1 if x is greater than 0. So I've turned it into my own piecewise function, or you can just think about it in terms of a graph. Either way, you'll still get the same answer, right? If I think about it in terms of a graph, I'm saying, okay, well, it's going to be between -5 to 3. You can think of it graphically and say, okay, well, between -5 is like right here, all the way to 0. That's going to be an area of -5 down here. And then if I go all the way from 0 to 3, I can say 0 to 3 is right here. It's going to be an area of 3, because it's going to be 3 times 1. And you can add these together to get an area of -2. So you can do it graphically like that, or you could do it algebraically. You can say algebraically, you can go, whoa, that was not supposed to happen. You can say it's -1, and it's a derivative of the integral of a constant, right? You can say that this is really, You can say this is really the integral between -5 to 0 plus the integral from 0 to +3. And you can say, on the left piece, I know I'm going to have -1. On the right piece, I know I'm going to have a +1. And then from there, you can do the antiderivative using the shortcut, right? The shortcut says you subtract the bounds. 0 minus a -5 is a +5. And I can even write out the shortcut, right? I'm going to say 0 minus a -5. All of this times whatever number I have here, which is a -1. Again, double negative means this is a positive, and 5 times a -1 is a -5. And I don't know why I did that in blue. Let's change it back to red. And then over here on this right-hand side, I can say, okay, the trick here is you subtract the bounds. 3 minus 0 is 3. And then you multiply it by whatever the number is right here. And that number is 1. So you can say this is 3 times 1, which is just 3. And I add those together, and I get a -2, which, again, I got in a very different way. And I kind of want to show this graph in the notes. I know I did in laser pointer, but I should really have this. I can say, maybe I can copy and paste this to show what the graph looks like, and also what I'm doing to it. So I can say that if I'm going and I'm continuing this line out a little bit, and I'll say that this spot here is -5, and this spot maybe right there is +3, and I can cut it off, and I can say this area is -5, and this area up here is a +3, and I can say that this height is 1, that height is a -1, and I can do that for this graph as well. Nice, nice, nice. Lots of good notes. Okay, number 12. Holy moly. This thing looks intense. It's our last question. I was like, I don't know if I can do another one after this. This looks hard. All right, so, oh my God, from -pi/2 to pi/2. All right, let's just go forward and see what happens. I'm going to have the integral between -pi/2 to 0, and then I'm going to add the integral from 0 to pi/2. Left function is 1 minus 2 sine of x. The right function is e to the power of -4x. All right, so do I have to worry about paying tax man? Yes, 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 yes. All right, so luckily for Trig House, there's our house. The inside of the house is 1, therefore inside the house is x, therefore dinner is 1. I don't have to pay taxman for this one, but on this one I do, because again, E house is tree house, so the house lives right here, and you can see that the inside of the house, the inner is -4x, therefore dinner is -4, which is not 1, so you have to pay the taxman. Let's go ahead and do our scratch work up here. I'm going to say u is equal to -4x, taxman is equal to, don't see them, so 1, and then u prime is going to be equal to -4, and therefore I'm going to pay the taxman that fraction of -1/4. So really this becomes, I'll do this in blue maybe, I'll pop this out and say, really this becomes the integral from 0 to pi/2 of -1/4, now e to the -4x. All right, so from here, we move on and we say, okay, take the antiderivative of each of these. Antiderivative of 1 is x. Antiderivative of 2 sine of x is going to be, okay, hold on. Anti-same means change. So instead of a negative sign, I'm going to have a positive sign. It's going to be 2 cosine of x. Again, this is going to be evaluation bar between -pi/2 all the way to 0. And this right-hand piece is, the lovely thing about E house is it stays E house, and you just rewrite a -1/4 e to the -4x, but you do evaluation bar between 0 and pi/2. Oh boy. All right, let's go ahead and start plugging things in. When I say x is equal to 0, what's going to happen? I'm going to get 0 plus 2 cosine of 0. And cosine of 0, just as a quick reminder, is right here. Cosine is how far right you've moved. You've moved right 1 unit. Therefore, cosine of 0 is 1. And I need to multiply 1 times 2, which is 2. And 0 plus a 2 is 2. So I can say this whole thing turned into 2. Not too bad. What happens when x is equal to the other bound, the start? This is going to be -pi/2, of course. And that's a little bit too sloppy of a pi. Let's make it look a little bit nicer. And then when I do that, I'm going to get -pi/2 plus 2 times cosine of the negative pi. Oh, come on, pi's. My pi's they don't want to write nice. Okay, negative pi over 2. All right, well, negative pi over 2 is interesting, right? Because normally pi over 2 positive goes this direction. A negative rotation is actually the clockwise direction, and negative pi over 2 actually lives right here. So let me go ahead and mark that point. Right here is negative pi over 2. Man, my pi's do not like writing nice today. And then from there, I can say cosine is how much left and right you're moving, and you're not moving left, nor are you moving right. Therefore, this whole thing turns into a 0, which is nice because I was worried about that yucky value, because 0 times 2 is 0, and therefore I only have to worry about the negative pi over 2. So I have negative pi, oh my goodness, negative pi over 2. Nice. And again, you're going to do this minus this value. Double negative means it's plus, so I really have a total area of 2 plus pi over 2 for my left piece. Time to move on to my right piece. Almost there, guys. Here we go. Okay, so when x is equal to positive pi over 2, let's see what happens. I'm going to get a negative 1/4 e to the power of negative 4 times pi over 2. I don't think that simplifies very nicely. It's still negative 1/4 e to the power of negative 2 pi. There's not much you can do with it. It stays like that. There's no evaluation. Okay, what happens when x is equal to 0? Again, very tempting to say it's 0, but it's not. Never with eHouse. Negative 1/4 e to the power of negative 4 times 0 now. Anything times 0 is 0, so this is really just... here, let's do some laser pointer. This is 0. Anything, e, or anything to the power of 0, this whole thing is just 1, and 1 times negative 1/4 is negative 1/4, negative 1/4. And again, you're going to subtract this. You're taking this minus this. Double negative means we're really adding that 1/4 on, and I have a negative 1/4 e to the negative 2 pi plus 1/4. And now I'm going to take the left piece and add it with the right piece. So, like terms, okay, there's some constant, right? 1/4 plus 2, this 2, I'm going to multiply by 4 over 4, so it's really 8 over 4, and I'm going to get 9 over 4. So my final answer is going to have a 9 over 4 in it. I have a 9 over 4. I'm going to add a pi over 2, and I'm also going to add, or I guess subtract, right, because it's minus 1/4 e to the negative 2 pi. And I guess if I want to be really cool, I can say, well, I can multiply those together, and I can really erase the 1 and move the e to the negative 2 pi up to the top of that. And ooh, yeah, that looks a lot nicer. And I'm noticing that, okay, yes, this is maybe going a little bit too deep here, but notice how these were, that's a 4, that's a 4. I could have made that a 4, and I could have put them all in the same fraction. So that might have been an answer, but I'm going to go ahead and multiply by 2, and watch this. I'm going to say this is really 9 plus 2 pi minus e to the negative 2 pi all over 4. Look at that. How cool is that? I don't know if that's going to show up on the multiple choice answer. It might show up as this one. Who knows? But that was a rough one. Wow. All right. That does conclude Worksheet 5-8 for AP Calculus AB. There's the second page. There's the first page. Thanks for watching.